Welcome to Numerical Methods for Scientists and Engineers with Pseudocodes. Video 1. Fundamental Initial Value Problem. A mathematical model, a set of governing differential equations describing a physical phenomenon of system, provides a theoretical prediction of a real-world physical event. Solving pertinent mathematical model of an event helps us to understand the problem or predict its behavior under certain circumstances. Initial value problems, IVPs, describe an unsteady behavior of a physical event for t greater than t0, provided that the solution is known at t equals t0, i.e., the initial value. In other words, the solution interval of the IVPs is semi-infinite. But numerical solutions are typically sought for a finite interval from t0 to an uppercase T value, or until a physical event reaches the steady state. The fundamental initial value problem refers to the problem of solving a differential equation with specified initial conditions, which is a foundational concept in the study of differential equations, particularly in physics, engineering, and mathematics. It involves finding the solution to a differential equation that satisfies both the equation itself and the given initial conditions at a specified point. An initial value problem takes the following general form, where alpha 0 through alpha n-1 are known constants that specify the initial state of the system at x equals x0. Consider a first-order ordinary differential equation as the fundamental initial value problem, expressed as follows. Where x is the independent variable, y is the dependent variable, fxy is a function describing the differential equation, and yx0 equals alpha 0 is a starting value called the initial condition, IC. A second-order initial value problem is a second-order ordinary differential equation with two initial conditions at x equals x0. High-order IVPs require as many initial conditions as the order of the initial value problem, e.g., the following third-order ODE has three initial values, where alpha 0, alpha 1, and alpha 2 are constants. The coefficients of the IVPs may be constants, a, b, c, and d, or they may be functions of the independent variable ax, bx, cx, and dx so on, as in the following differential equation. The differential equations like the one presented above are termed linear ordinary differential equations. If at least one of the coefficients of the ODE involves a dependent variable and/or its derivatives, the ODE is referred to as a nonlinear ordinary differential equation. The following is an example of a nonlinear ordinary differential equations or initial value problem, where a equals 2, b equals e to the x plus y, and c equals square root y plus y prime squared. The mathematical model of a damped motion of a mass m attached to a spring of length L is given as follows, where k is the spring constant, b is the damping coefficient, and y is the vertical displacement, relative to the equilibrium position. A motion is set when the attached mass is pulled down by an amount L and then released at t equals 0. The vertical displacement and velocity before the mass is released are the initial conditions. That is, the displacement is downward by L, and the mass is at rest, i.e., 0 velocity. A typical damped motion of the mass spring system is shown in the figure. After sufficient time, the system reaches steady state. The mathematical model of a swinging motion of a pendulum of mass m and length L is given as follows, where the dependent variable theta is the angle from the vertical to the pendulum, also referred to as amplitude. The independent variable t denotes time, and g is the acceleration of gravity. Pendulum is positioned at theta equals pi over 4, and the angular speed omega is 0 before the pendulum is released. So these make up the initial values. This is a nonlinear initial value problem due to having sign of dependent variable theta. A typical undamped motion is depicted in the figure. In the textbook and this video series, the first-order IVPs are used mostly for several reasons to explain numerical methods for initial value problems. The first-order IVPs are simpler to understand and work with. They provide a foundation for generalizing methods to higher-order ODEs and systems of equations. The core principles of numerical analysis, such as step size, error, stability, and convergence, are more easily illustrated with first-order problems. Many real-world systems can be modeled by first-order equations or reduced to first-order systems. Hence, the first-order IVPs are a natural starting point for introducing the concepts of numerical solution techniques. That is all for now. See you next time with another topic. Bye.